Today's topic is research design, and more specifically, the difference between experiments and observational studies. Culturally, we put a lot of weight on the idea of running experiments. One Google image search for experiment will give you all kinds of crazy stock photos of beakers with smoke and mysterious colors and anything slightly reminiscent of 7th grade science class. But experiments do have a technical definition in science, and it's worthwhile distinguishing them from observational studies, which are more than just a study that includes observation. Today we'll take a look at these two broad categories of research design to better understand what they mean and how your design relates to what conclusions you can reasonably draw. We'll start with experiments. A defining feature of experimental design is that something is experimentally manipulated. What does that mean? Well, it means that there was a specific aspect of the research that was selected and changed by the researcher to specifically identify whether or not that particular manipulation changed something else. That's a lot of words. It's more intuitively understood by examples. So we all know that werewolves can be killed by silver bullets. But what if we wanted to treat lycanthropy, perhaps with a silver-based medication? An experiment to test this would be if we rounded up some werewolves and gave some of them a dose of silver and asked the rest of them to avoid silver at all costs. Here, the experimental manipulation is exposure to silver. We are specifically choosing some people to receive silver and some not to receive silver so that we can directly compare those two specific groups. And then by the next full moon, we might be able to tell if silver made a difference based on how many turn into werewolves, so long as the sample size is large enough. A key aspect to inferring causality from experimental design is randomization. The comparison between the experimental group and the control group only works if we randomly select who gets silver and who gets nothing to act as a control, so that we're isolating the differences between groups based on that one manipulation. If we don't randomize the treatment and control, then that might introduce bias, and it certainly induces some uncertainty. Maybe all the married werewolves are scared they will hurt their family, so they all ask to be in the silver condition. The silver condition no longer represents the dose of silver alone, but rather it also represents what other patient characteristics are associated with being a married werewolf. This is why extra measures are often taken to ensure proper randomization. So when we say a double-blind trial, for example, that means neither patients nor experimenters know who is in the control group and who is in the experimental group. This helps make sure that the only difference between groups is the experimental manipulation. We'll never be certain that randomization worked, but going out of our way to isolate differences due to the manipulation alone helps build credibility and causal inference from experiments. A non-experimental approach is called an observational study. In an observational study, we just don't have that experimental manipulation, but rather we look at what happens to patients who have similar experiences. There are a few ways we can think about observational studies. One is a cohort study. Here we look at a cohort, or a group of people who have a common connection, and we see how their experiences compare over time. Using the werewolf example, this would be like if we found everybody bit by a werewolf on Halloween this year and kept track of their daily experiences. We would note who winds up exposed to silver in their daily life, and we would note who isn't exposed to silver in their daily life. And then, when the full moon comes around, we could see how many of them turn, see if there are meaningful differences there. It's important to note that we can't say that this is necessarily a causal relationship because we didn't choose who has the silver and who doesn't. But we can understand how silver related to the probability of turning into a werewolf. Another approach is a case control study. Here we look at people who have a certain trait, the case group, and we see how they compare to people who lack that trait, the control group. This would be like if we gathered together a panel of werewolves and asked them, "Have you been exposed to silver recently?" Then we could make the comparison of how often they turn into werewolves between those who have been exposed to silver and those who have not. This is different than a cohort study because we are looking at the cases and controls at one point in time, a cross-section of their regular experiences. While there are pros and cons to each of these designs, most important is keeping in mind broadly what conclusions can reasonably be drawn from each design. We often want to make a causal conclusion, but that can be hard to do. The best chance at concluding that there are causal relationships is within an experimental design, and this is important when randomization is successful. Even if you include an experimental manipulation in the design, that's no guarantee that causal effect can be identified. If a significant number of patients, for example, realize that they're in the control condition and they decide they don't want to be in the study anymore, that biases the results. Alternatively, if the experimental group doesn't adhere to the treatment that they're prescribed, well, then you haven't tested the treatment you wanted to test. Lastly, if the sample size is small, a non-significant difference between the groups may be because of the small sample size, rather than a true null effect. Scrutinizing the quality of randomization and the implications for the results is necessary to understanding how causal the conclusions may be. Even if randomization doesn't go well, or if an observational study is performed, that still possibly could be a meaningful analysis. We just shouldn't conclude that there's a causal relationship there. It's worthwhile to understand how associations are between which variables in which directions, but we just shouldn't imply that they're directly causally related. You need to ask yourself, what are the underlying causal mechanisms, even if we haven't tested them right now? Is there an unmeasured trait that induces an association? Or could an experimental design indicate true causality even if you didn't have an experimental design in this specific study? Understanding the strength of associated relationships can be insightful for contextualizing broader implications of research, but you need to be judicious in implicating causal relationships. It may still be worthwhile understanding how medical traits relate, but we need to be thoughtful about when we consider them to be causal relationships. Thank you for tuning in. My name is Ray. My email is on the screen if you have any follow-up questions, as well as there's the URL for the Biostatistics core. We're happy to help you. Just sign up for a meeting on the website. Thank you very much.